Imagine staring into the night sky, knowing that among those countless points of light, some of them aren't just stars, they are cosmic ghosts. The remnants of dead stars, white dwarfs, linger in the darkness, emitting signals that defy everything we think we know about the universe. These aren't just whispers from the void, they are full-blown cosmic enigmas, pulsing with mysteries that leave even the brightest astronomers scratching their heads. What if I told you that these celestial relics aren't just quietly fading away? Instead, they're sending out bizarre, unexplained signals, 25 of them, each one a puzzle begging to be solved. White dwarfs are the ancient skeletons of stars like our Sun. After burning through their fuel, they collapse into dense, Earth-sized embers glowing faintly with leftover heat. But here's the thing, they shouldn't be doing much else. Yet, over and over, we've caught them behaving in ways that make no sense, strange flickers, unexplained bursts of energy. Patterns that look almost intentional. It's as if these dead stars are trying to tell us something, and we're only just beginning to listen. The more we observe them, the more questions they raise. Why are some white dwarfs spinning at impossible speeds? How are others emitting signals that resemble artificial broadcasts? And what could possibly explain the eerie, rhythmic pulses that seem to defy the laws of physics? This isn't just about scientific curiosity, it's about confronting the unknown in its purest form. Every unexplained signal from these white dwarfs is a crack in the foundation of what we think we understand about the universe. Some of these mysteries might have natural explanations hidden in the fabric of space-time. Others, well, they might force us to rethink everything. So today, we're diving deep into these 25 enigmatic signals, unraveling the stories behind each one, and exploring what they could mean for our place in the cosmos. Buckle up, because by the end of this journey, you'll see the night sky a little differently. And who knows, you might just find yourself staring up, wondering what else these cosmic ghosts are trying to say. The first signal that shook the scientific community came from a white dwarf nearly 1,300 light-years away, pulsing with a rhythm that shouldn't exist. Dubbed the pulsating enigma, this signal wasn't just unusual, it was a direct challenge to our understanding of stellar remnants. Most white dwarfs cool quietly, their light fading in predictable ways. But this one, it flickered like a cosmic lighthouse, emitting bursts of energy in a precise, repeating pattern, a heartbeat in the void. Astronomers first detected it in 2017, buried in data from the Kepler Space Telescope. At first, they assumed it was interference or a technical glitch, but the signal persisted, showing up again and again with eerie consistency. What made it truly baffling was its frequency, a rapid, regular pulse every 1.37 minutes like clockwork. White dwarfs aren't supposed to behave this way. Their spin rates and energy outputs are governed by well-tested physics, yet here was one breaking all the rules. The strangest part, the signal's intensity varied in a way that defied natural explanations. Normally, pulsations from white dwarfs are caused by internal vibrations or magnetic fields, but those follow predictable waveforms. This pattern was different, sharper, cleaner, almost engineered. Some researchers even double-checked their equipment, convinced it had to be an artifact. But the more they studied it, the clearer it became. This was real. So what could be causing it? One theory suggests an unseen companion, maybe a planet or a brown dwarf, tugging on the white dwarf's magnetic field like a celestial puppet master. Another idea points to exotic physics, crystals of oxygen and carbon forming in the star's core, creating seismic ripples we've never observed before. And then there's the more speculative possibility. Could this be something beyond our current models entirely? The pulsating enigma doesn't just ask questions, it forces us to reconsider what we know about the afterlife of stars. This signal isn't just a curiosity, it's a reminder that the universe still holds secrets we can't yet explain. And if a single white dwarf can defy expectations so boldly, what else might be out there waiting to be discovered? The pulsating enigma's strange rhythm has sparked fierce debates among astrophysicists, with theories ranging from the plausible to the mind-bending. One leading hypothesis involves quantum mechanics playing tricks on a cosmic scale. Deep within the white dwarf's core, atoms might be forming bizarre crystal structures under extreme pressure. Not ordinary crystals, but lattices of oxygen and carbon atoms so densely packed they vibrate like tuning forks. These quantum vibrations could theoretically produce rhythmic energy bursts matching the observed signal. But here's the catch: no known model predicts vibrations this precise or powerful. It's like hearing a bell ring in a vacuum. The sound shouldn't carry, yet it does. Another camp points to magnetic monsters lurking in the star's corpse. White dwarfs can have magnetic fields millions of times stronger than Earth's, twisting space-time around them like invisible whirlpools. If this particular dwarf has a lopsided magnetic field, perhaps warped by a nearby object, it might channel energy in focused jets, creating lighthouse-like pulses. Astronomers have seen similar behavior in neutron stars, but never in something as dense and cold as a white dwarf. The mystery deepens when you consider that magnetic fields should weaken over time, yet this signal remains stubbornly consistent. Then there's the planetary disruption theory. Imagine a surviving planet, its orbit decaying as the dying star expelled layers of gas. Now, the white dwarf's gravity shreds this world inch by inch, its debris spiraling into the star like cosmic raindrops. Each time a fragment impacts, it could trigger a burst of energy, but calculations show these impacts would be chaotic, not the metronome-perfect beats we're observing. Unless, of course, the debris is in some kind of resonant orbit, a gravitational dance we've never witnessed before. The most controversial ideas venture into uncharted territory. Some researchers speculate about phase transitions in the star's interior, entire regions of matter flipping between states like a cosmic switch, releasing energy in predictable spikes. Others whisper about quantum vacuum fluctuations, where particles blink in and out of existence in ways that might amplify certain frequencies. And yes, a few have dared to mention the possibility of non-natural origins, though most dismiss this as science fiction. Yet the signal's artificial-seeming precision keeps the question lingering at the edges of respectable debate. What makes the pulsating enigma so thrilling and frustrating is how it dodges every attempt at classification. It's not quite a variable star, not quite a pulsar, and definitely not anything we've catalogued before. Every new observation seems to add another layer of mystery. For instance, recent data revealed subtle harmonics in the signal, fainter pulses riding the main frequency like echoes in a cathedral. These could hint at complex internal structures or entirely new physics. The debate rages because at its core, this isn't just about one weird star, it's about the limits of our knowledge. If white dwarfs can behave this way, what else have we missed? Could there be a whole zoo of exotic stellar phenomena hiding in plain sight? Every time we think we've nailed down the rules of the universe, something like the pulsating enigma comes along to remind us the cosmos loves a good plot twist. The repeating whisper is the kind of cosmic anomaly that keeps astronomers awake at night, not because it's loud or flashy, but because of what it refuses to tell us. Discovered in 2019 by the European Space Agency's Gaia satellite, this signal comes from a white dwarf over 2,000 light-years away, pulsing with bursts of energy that follow no discernible pattern. Unlike the steady heartbeat of the pulsating enigma, the repeating whisper stutters, sometimes firing off multiple bursts in an hour, then falling silent for days. It's as if the star is speaking in a language we can't decipher, leaving behind clues without a key. What makes this signal so baffling is its inconsistency. Most cosmic phenomena, even the unpredictable ones, follow some rough statistical rules. Supernovas flare and fade, pulsars spin with regularity, but the repeating whisper defies those expectations. Its bursts vary wildly in strength, duration, and timing. One might last milliseconds, another lingers for minutes. The only certainty is that they will happen again, just never when or how you'd expect. Researchers first dismissed it as random noise, but the pattern, or lack thereof, became undeniable. When they mapped the bursts over time, they noticed something eerie. While irregular, the signal clustered. Weeks of silence would be broken by a flurry of activity, like a dormant radio suddenly crackling to life. This ruled out simple explanations like stellar flares or collisions with debris. Even magnetic reconnection, a process where twisted magnetic fields snap and release energy, couldn't account for the abrupt starts and stops. So what's really going on? One provocative theory involves tidal forces. If the White Dwarf has a hidden companion, a rogue planet, or even another star, their gravitational dance could be stirring up the dwarf's magnetic field. Picture a spoon swirling honey. As the companion orbits, it might twist the star's magnetic lines until they snap, releasing energy in a regular burst. The clustering could then reflect the companion's elliptical orbit, with activity spiking during close approaches. But here's the problem. No such companion has been detected, and the signal's randomness doesn't quite match tidal models. An even wilder idea floats: the possibility of a shattered asteroid belt. Imagine the remnants of a planetary system where countless fragments drift in unstable orbits. As these chunks collide or plunge into the White Dwarf, they could trigger sporadic bursts. Yet this doesn't explain the signal's sharp, almost clean energy signatures. Impact events tend to be messier, like cosmic fireworks, not the precise chirps we're observing. Then there's the outlier hypothesis: quantum tunneling in the star's core. Under unimaginable pressure, particles might occasionally tunnel through energy barriers, releasing sudden bursts of radiation. It's a long shot. No known physics predicts quantum effects on this scale. But when faced with the unexplainable, even fringe ideas get a seat at the table. The repeating whisper is more than a puzzle. It's a mirror held up to the gaps in our knowledge. Every time we think we've pinned it down, it slips away, taunting us with its randomness. And that's what makes it so thrilling. In a universe where we've grown accustomed to decoding patterns, this signal reminds us that some things refuse to fit neatly into boxes. Maybe that's the point. Not every whisper is meant to be understood. Maybe it's just there to remind us how much we still have to learn. While the repeating whisper defies easy explanation, its strangest feature isn't just its randomness, it's the way its energy behaves. Most white dwarfs emit a steady, fading glow as they cool over billions of years, like embers from a long-extinguished fire. But this signal's bursts spike with energies that shouldn't be possible for such an old, dense object. Imagine flicking a light switch and instead of a steady beam, the bulb flares unpredictably, sometimes a dim flicker, other times a blinding flash. That's the level of inconsistency we're dealing with here. To grasp how unusual this is, consider a typical white dwarf's life cycle. After shedding its outer layers, it settles into a quiet retirement, radiating heat uniformly as it slowly crystallizes into a celestial diamond. But the repeating whisper isn't following the script. Its bursts pack the energy of a stellar tantrum, releasing sudden spikes that rival younger, more active stars. Spectroscopic analysis reveals something even weirder. The bursts aren't just random in timing, they're erratic in composition. Some are dominated by X-rays, others by radio waves, as if the star can't decide which wavelength to use. This isn't just academic curiosity. These energy patterns challenge our fundamental models of stellar evolution. One leading theory suggests magnetic reconnection, a process where tangled magnetic field lines snap and release energy, could be responsible. We've seen this on the Sun during solar flares, but white dwarfs aren't supposed to have the internal dynamos to sustain such activity, unless, of course, something's reviving them. Could a nearby object, a surviving planet, or a stealthy brown dwarf be injecting fresh chaos into the system? The hunt for answers is driving new observations. The James Webb Space Telescope recently turned its infrared eye toward this enigma, searching for heat signatures of hidden companions. Meanwhile, the upcoming Vera C. Rubin Observatory plans to monitor the White Dwarfs region with unprecedented precision, hoping to catch its bursts in real time. There's even a proposed mission called Star Sweep, designed to study white dwarf magnetic fields in detail, because if there's one thing the repeating whisper has taught us, it's that we've underestimated these cosmic retirees. But the most tantalizing clue might come from an unexpected source: quantum physics. Some researchers speculate that under the extreme pressures inside a white dwarf, particles could form Cooper pairs, a phenomenon usually seen in superconductors, creating sudden energy releases when these pairs break. It's a fringe idea, but then again, so were black holes once. What makes this signal so compelling is its refusal to fit into neat categories. It's not a pulsar. It's not a flare star. It's something entirely new, lurking in data we've had for years. Every time we think we've cornered an explanation, the whisper throws another curveball, and that's why astronomers can't look away. Because in the end, it's not just about solving a puzzle, it's about rewriting the rules. Some signals shout, others fade, but the silent scream does something far stranger. It explodes into existence with a burst of energy so fierce it briefly outshines its host white dwarf, only to vanish without a trace, leaving behind a silence so profound it feels almost deliberate. Detected in 2021 by the Atacama Large Millimeter Array in Chile, this signal lasted just 42 seconds, a cosmic blink that upended everything we thought we knew about white dwarf behavior. What makes the silent scream so unsettling is its sheer violence followed by absolute quiet. Most stellar outbursts like flares or nova eruptions leave lingering afterglows or recurring activity. But this one moment, the white dwarf was a placid dot in the constellation Cygnus. The next, it unleashed an X-ray spike 1,000 times its normal brightness. Then nothing, no fading echo, no follow-up pulses, just the empty hum of space, as if the star had never screamed at all. Astronomers scrambled to explain it. Initial theories pointed to a cataclysmic event, perhaps a rogue asteroid's final plunge, vaporized instantly on impact, but the energy signature didn't match. Impacts produce messy, broadband radiation, while the silent scream's emission was unnervingly focused, almost laser-like. Others suggested a magnetic reconnection event, where the star's twisted magnetic field suddenly realigned. Yet those typically produce secondary bursts like aftershocks, not this eerie radio silence. The most compelling and controversial explanation involves quantum vacuum decay, a hypothetical phenomenon where a bubble of true vacuum forms in space-time, releasing a burst of energy as it expands. In simpler terms, the white dwarf might have briefly tapped into a fundamental force we've never directly observed. It's the kind of idea that straddles the line between physics and philosophy, because if true, it implies the star stumbled upon a universal off switch we didn't know existed. But here's the real kicker: the silent scream wasn't a one-off. 6 months later, a second white dwarf in Draco did the exact same thing. Same burst profile, same abrupt silence. Suddenly, astronomers faced a chilling possibility. What if this isn't a fluke but a phase, a previously invisible stage in a white dwarf's life cycle, where dying stars convulse once before going dark forever? This signal forces us to confront how little we truly understand about stellar endings. White dwarfs were supposed to be predictable, fading quietly into the cosmic background. The silent scream tells a different story, one where even in death, stars might have secrets volatile enough to shake the heavens. And the most haunting question remains: if we'd blinked, would we have missed it entirely? The ghostly echo doesn't just arrive, it lingers. This signal, detected from a white dwarf in the constellation Lyra, pulses with a bizarre delay, as if the universe itself is playing tricks with time. Astronomers first noticed it in 2022, a sharp burst of radio waves followed by faint, repeating copies of itself, each one arriving seconds later than it should. It's like shouting into a canyon and hearing your voice bounce back from walls you can't see. But here's the catch: there are no walls, no nearby nebulae, no dense dust clouds, nothing to explain why this signal keeps echoing into the void. What makes the ghostly echo so unnerving is its precision. The delays aren't random, they follow a clear sequence like footsteps in the dark. The primary burst hits our telescopes, then exactly 3.2 seconds later, a weaker copy appears. Then another, fainter still, after another 3.2 seconds. This isn't just scattering or interference. It's as if something out there is rebroadcasting the signal, note for note, but with a cosmic delay. Theories abound, but none fit perfectly. One camp points to the interstellar medium, the thin soup of gas and dust between stars. Normally, it might scatter radio waves slightly, but never with such rhythmic precision. Unless, of course, the white dwarf sits near an invisible structure, a cold molecular cloud or a filament of dark matter we can't yet detect. Another idea invokes gravitational lensing, where the signal bends around a hidden mass, a rogue black hole or a neutron star, creating multiple ghost images of the original pulse. But even that struggles to explain the echo's perfect timing. Then there's the wild card, quantum foam. Some physicists suggest space-time itself might not be smooth at microscopic scales. If the signal passed through a region of frothy, fluctuating space-time, could it have fractured into echoes? It's a stretch, but when conventional answers fail, even fringe ideas get a hearing. The most tantalizing clue came last year when the same white dwarf emitted a second ghostly echo, this time with a different delay interval. Suddenly, the echoes weren't just repeating, they were evolving. Whatever's causing this isn't static, it's changing, reacting, or maybe even learning. That's the kind of realization that sends a shiver down an astronomer's spine. Because if we're not just hearing echoes but conversations, then who or what is on the other end? The binary paradox isn't just a mystery, it's a cosmic contradiction. Nestled in the constellation Scorpius, a white dwarf locked in a gravitational dance with a companion star emits signals that defy every textbook rule of binary systems. Normally, when two stars orbit each other, their interactions follow predictable rhythms: tidal forces, material transfers, synchronized rotations. But this pair, they're breaking the rules in broad daylight. The white dwarf's pulses arrive with a cadence that shouldn't exist, as if the companion star's presence is somehow rewriting physics on the fly. Here's what makes it so baffling. The white dwarf's emission patterns suggest it's being fed by its companion, a common scenario where one star siphons material from the other. But the energy signatures tell a different story. Instead of the steady, heated glow of accreting matter, this dwarf fires off erratic bursts, some weaker than expected, others blazing with impossible intensity. It's like watching a fire hose hooked up to a sprinkler system, alternating between a trickle and a geyser. The companion star, a run-of-the-mill red dwarf, simply doesn't have the mass or activity to explain these wild fluctuations. Astronomers first blamed gravitational stripping, the idea that the white dwarf's fierce gravity was tearing gas from its neighbor in uneven clumps. But simulations showed this would create a more chaotic signal, not the oddly structured pulses we're seeing. Then came the magnetic twist theory. Perhaps the companion's magnetic field was funneling material into focused streams, creating bursts when these streams hit the dwarf's surface. Yet detailed observations revealed no magnetic activity strong enough to pull this off. The real curveball came when researchers noticed the pulses weren't just irregular, they were anticorrelated with the companion's rotation. When the red dwarf's active side faced the white dwarf, the signals dimmed. When it turned away, the dwarf flared up. This inverse relationship makes zero sense in standard models. If anything, closer proximity should amplify interactions, not suppress them. Now, theories are venturing into uncharted territory. One radical idea proposes that the white dwarf's own magnetic field is creating a kind of cosmic feedback loop, reflecting energy back onto the companion in ways that disrupt normal accretion. Another suggests the system might be harboring a hidden third object, a rogue planet or brown dwarf, tugging on both stars like an invisible puppeteer. But the most provocative hypothesis, that we're seeing evidence of resonant harmonics where the star's orbital frequencies interact to amplify or cancel out certain emissions, a phenomenon only predicted in theoretical papers until now. The binary paradox isn't just challenging assumptions, it's exposing gaps in our understanding of how stars communicate. If a simple two-star system can behave this unpredictably, what does that mean for the thousands of other binaries we've catalogued? Are we missing something fundamental, or is this pair a celestial outlier? Every new observation deepens the mystery, proving that even the most familiar cosmic duets can still surprise us, and that's what makes this signal so thrilling. It's not just a puzzle to solve, it's a reminder that the universe always keeps a few aces up its sleeve. The temperature anomaly isn't just breaking the rules, it's rewriting them. Imagine a star that's been dead for billions of years, cooling steadily like a forgotten ember, when suddenly, without warning, its surface temperature spikes by thousands of degrees. That's exactly what astronomers observed in a white dwarf 2,500 light-years away, tucked into the constellation Cassiopeia. In 2023, the Hubble Space Telescope caught this cosmic retiree doing the impossible, heating back up as if it had found a hidden fountain of youth. What makes this so baffling isn't just the temperature jump, it's the speed. Over just 6 months, this white dwarf's surface went from a predictable 18,000 degrees Celsius to a blistering 24,000. That's like a corpse suddenly sitting up and breaking into a sprint. Even more puzzling, there was no visible trigger, no nearby stars dumping energy into it, no asteroid impacts, no accretion disks. Just a silent, inexplicable reheating event that defies every model of stellar decay we've ever built. Standard theory says white dwarfs cool in a slow, linear fashion, their heat radiating away as they crystallize into ultra-dense spheres of carbon and oxygen. But this star, it zigzagged. Spectroscopic data revealed something even stranger. The heating wasn't uniform. Parts of its surface flared hotter than others, creating a thermal patchwork that resembled a cosmic bruise. Some regions glowed like freshly forged metal, while others stayed cool, as if the star's energy were being funneled through invisible channels. Astronomers first scrambled to blame hidden nuclear reactions, maybe residual fusion reignited in the star's core. But white dwarfs lack the mass to sustain such processes. Their fusion days are long over. Others pointed to gravitational energy release, where settling heavier elements might generate heat. Yet calculations showed this would produce a gradual warming, not the violent spikes observed. The leading theory now involves magnetic turmoil. If the white dwarf's interior is laced with ultra-strong magnetic fields, they could be rearranging themselves, twisting and snapping like rubber bands under tension. This magnetic reconnection might inject sudden bursts of energy into the star's outer layers, but even that doesn't fully explain the localized heating or the sheer intensity of the temperature swings. And then there's the outlier idea, quantum phase transitions. Deep inside the dwarf, atoms might be shifting into exotic crystalline configurations, releasing stored energy in erratic surges. It's a stretch, but when conventional physics falls short, even fringe concepts get a hearing. What's undeniable is that this anomaly forces us to question one of astronomy's oldest assumptions, that dead stars fade quietly. Because if they can suddenly reheat themselves, who's to say they can't do worse? The magnetic mystery isn't just bending the rules, it's snapping them in half. Most white dwarfs with magnetic fields behave like cosmic compass needles, their polarization steady and predictable. But this one, located in the constellation Ursa Major, flips the script entirely. Its magnetic field doesn't just fluctuate, it convulses, shifting strength and orientation in violent, erratic swings that leave astronomers reeling. Picture a lighthouse where the beam doesn't just rotate but morphs into entirely different shapes mid-spin, defying every law of electromagnetic stability we know. What sets this signal apart is its sheer unpredictability. Typical magnetized white dwarfs pulse with rhythmic precision, their fields waxing and waning over hours or days. But the magnetic mystery, it can shift from a relatively weak 1000 Gauss to a staggering 100 million Gauss in minutes, then collapse back just as fast. Even stranger, these fluctuations don't correlate with the star's rotation or any visible external triggers. It's as if the star's magnetic personality is having a crisis, one moment calm, the next erupting in cosmic rage. The first clue to this enigma came in 2022 when the Chandra X-ray Observatory caught the white dwarf emitting bizarre, polarized bursts. Normally, X-rays from magnetic stars follow orderly patterns tied to their spin. These bursts, though, were all over the map, some tightly focused, others scattering like shrapnel. Spectrographs revealed something even more unsettling. The star's magnetic axis wasn't just wobbling, it was migrating, drifting across the surface like a wandering North Pole. Theories to explain this chaos range from the plausible to the borderline fantastical. One camp argues for internal magnetic earthquakes, where the star's crystallized crust fractures under stress, releasing pent-up energy in violent rearrangements. Others point to a hidden dynamo effect, perhaps a layer of swirling metallic hydrogen beneath the surface, acting like a rogue generator. But the most provocative idea involves external manipulation, an unseen black hole or neutron star nearby, its gravity warping the white dwarf's field lines like invisible fingers kneading dough. The implications stretch far beyond this one star. If magnetic fields can become this unstable, it forces us to rethink how stellar remnants evolve. Could these fluctuations explain other unexplained signals? Might they even hint at new forms of energy transfer in dead stars? Every time we observe this white dwarf, it throws another curveball, and that's what makes it irresistible. Because in the end, the magnetic mystery isn't just a puzzle to solve. It's a window into the untamed, volatile heart of the cosmos itself. The dark pulse isn't just mysterious, it's invisible. Most cosmic signals announce themselves with flashes of light or bursts of radiation, but this one, it exists only in the shadows, detected solely in radio waves and infrared, with no trace in the visible spectrum. It's like hearing a scream in a pitch-black room but finding no one or nothing there when you turn on the lights. Discovered in late 2023 by the Very Large Array in New Mexico, this signal comes from a white dwarf in the constellation Andromeda, pulsing with eerie regularity, yet leaving no optical footprint whatsoever. What makes the dark pulse so unsettling is its purity. Most celestial objects emit across multiple wavelengths, heat, light, radio, but this white dwarf defies that rule. Optical telescopes see only a dim, cooling ember, while radio antennas pick up sharp, rhythmic bursts every 4.1 hours. It's as if the star has two separate identities, one for the seen universe, another for the unseen. The lack of visible counterparts rules out common explanations like stellar flares or accretion disks. Even stranger, the pulses aren't just consistent. They're clean, devoid of the static or distortion usually caused by interstellar dust or plasma. Astronomers initially suspected a hidden companion, maybe a neutron star or black hole, swinging around the white dwarf and emitting radio waves as it orbits. But detailed searches found no gravitational wobbles in the system, no telltale tugs on the dwarf's motion. Another theory points to exotic matter interactions within the star itself. Under unimaginable pressures, the dwarf's crystallized core might be generating superconducting currents, creating magnetic loops that funnel energy into focused radio jets. It's a stretch, but so is every other idea when faced with a signal that refuses to play by the rules. Then there's the truly radical possibility, action conversion. Some particle physicists theorize that hypothetical particles called actions invisible, lightweight, and abundant in dense stellar environments could convert into radio waves under intense magnetic fields. If this white dwarf's magnetism is just right, it might be acting as a natural action factory, its interior churning out dark particles that transform into the very pulses we detect. No one's ever proven actions exist, but no one's ever found a better explanation for the dark pulse either. This signal doesn't just challenge our tools, it challenges our perception of reality. If a star can whisper in wavelengths we can't see, what else is hiding in plain darkness? The dark pulse forces us to confront an unsettling truth. The universe might be far louder than we realize. We've just been listening to the wrong channels. The age to fear is the cosmic equivalent of finding a pensioner running marathons. It shouldn't be possible, yet there it is. Nestled in the constellation Perseus, this white dwarf emits energetic bursts that scream youth, but its cooling rate and spectral fingerprints tell a different story. This star is ancient, an elder of the galaxy that should have settled into quiet retirement eons ago. Discovered in 2024 by the Sloan Digital Sky Survey, this dissonance between age and activity has astronomers questioning whether we've misunderstood stellar aging altogether. Here's the problem: white dwarfs are stellar tombstones. Once they exhaust their nuclear fuel, they gradually cool over billions of years, their light dimming predictably like a dying ember. But the age to fear's emissions pulse with the vigor of a much younger object. Ultraviolet flares erupt from its surface, and its X-ray output rivals white dwarfs 10 times its age. It's as if a fossil suddenly started breathing. Initial theories pointed to observational error, perhaps light from a nearby star was contaminating the data. But follow-up studies with the Hubble and Chandra telescopes only deepened the paradox. Not only is the age to fear genuinely old, around 8 billion years, based on its cooling curve, but its violent activity is undeniably coming from the dwarf itself. Spectroscopy revealed heavy elements like iron and silicon in its atmosphere materials that should have sunk into its core long ago under the star's immense gravity. Their presence suggests something is churning the dwarf's interior, dredging up buried elements like a cosmic blender. One explosive explanation involves late-stage nuclear burning. While most white dwarfs abandon fusion as they die, a few might retain pockets of hydrogen in their outer layers. If this star somehow reignited these reserves, it could briefly mimic youthful activity. But the math doesn't add up. The energy required would vaporize the remaining fuel in millennia, not sustain bursts over billions of years. Another camp suspects a hidden companion, a Jupiter-sized planet, perhaps, whose decaying orbit injects fresh material into the dwarf's atmosphere. As the planet's gases spiral inward, they could trigger sporadic fusion, creating the illusion of youth. The hitch: no such planet has been detected, and the star's motion shows no gravitational wobbles to suggest an unseen partner. The most radical theory: quantum tunneling on a stellar scale. Under the extreme pressure inside an aging white dwarf, atomic nuclei might occasionally bypass classical energy barriers, allowing fusion to occur even in ultra-cold environments. It's the stellar equivalent of a frozen battery suddenly delivering a jolt possible in quantum mechanics, but never observed at this scale. If true, it would mean white dwarfs never fully die. They just become dormant, capable of flickering back to life under the right conditions. What makes the age to fear so unsettling isn't just the mystery, it's the implications. If one white dwarf can cheat time, how many others are masquerading as youthful when they're actually ancient? Our entire cosmic clock for dating stellar populations might need recalibration. And that's the real revelation here. Sometimes the universe doesn't just hide its secrets, it rewrites them right in front of us. The fast fader doesn't just disappear, it evaporates. Most white dwarf signals flicker, fade, or fluctuate over hours, days, even years. But this one, it's here 1 second, gone the next, vanishing faster than a shooting star. Detected in 2024 by the Transiting Exoplanet Survey satellite, this signal erupted from a white dwarf in the constellation Aquila, blazing brightly for exactly 26 seconds before dissolving into nothingness. No gradual dimming, no residual glow, just a cosmic light switch flicked off mid-pulse, leaving astronomers staring at empty data streams and scrambling for explanations. What makes this signal so unnerving is its abruptness. White dwarfs are the universe's slowest burners, cooling over billions of years with glacial patience. Even their most violent outbursts like flares or accretion events leave lingering traces like echoes in a canyon. The fast fader defies that logic. Its light curve doesn't taper, it plummets, dropping from peak brightness to total darkness in under 3 seconds. That's faster than some supernova remnants fade, and those involve explosions 1,000,000 times more energetic. Initial theories blamed equipment error, a satellite glitch or cosmic ray interference. But multiple telescopes, from radio arrays to X-ray observatories, caught the same vanishing act. The signal was real, and its disappearance was anything but artificial. So what could snuff out a stellar signal so abruptly? One leading hypothesis involves photodissociation fronts, ultra-dense shells of gas around the white dwarf that absorb and dissipate energy almost instantly. Picture a pane of glass shattering under a spotlight. The light doesn't fade, it just stops. If the dwarf's atmosphere is layered with such material, a sudden flare could trigger a cascading collapse, swallowing its own energy before it escapes. Another idea points to relativistic jets. If the white dwarf's magnetic field channeled a burst of particles at near light speed, the jet could have pointed directly away from Earth mid-eruption, creating the illusion of a sudden cutoff. But jets that precise are the domain of neutron stars and black holes, not retiree stars like white dwarfs. Then there's the quantum vacuum hypothesis. Under extreme magnetic conditions, space itself might act like a cosmic sponge, soaking up emitted photons before they reach us. It's a fringe idea, but when conventional physics fails, even the wildest theories get a hearing. The fast fader's true legacy isn't just the mystery, it's the implication. If white dwarfs can vanish signals this abruptly, how many other cosmic flashes have we missed? Are these events rare, or have our telescopes simply been too slow to catch them? Every unanswered question is a reminder. The universe operates on scales we're only beginning to perceive. And sometimes the most profound messages aren't in the light, but in the darkness that follows. The cosmic synchronizer doesn't just pulse, it harmonizes. This white dwarf, located in the constellation Orion, emits bursts of energy that align with distant cataclysms across the cosmos, as if it's keeping time with the universe's most violent events. Detected in late 2024 by a network of observatories, its signal first raised eyebrows when researchers noticed an eerie pattern. Every time this dwarf flared, a supernova or gamma ray burst erupted somewhere else in the observable universe within days. Not just once or twice, over a dozen documented instances, with statistical analysis suggesting the odds of this being pure chance at less than 1 in 10,000. At first glance, it sounds like cosmic pareidolia, the human tendency to find patterns where none exist, but the data refuses to dismiss it so easily. Take one striking example. On March 8, 2025, the synchronizer released a sharp X-ray spike. 72 hours later, a supernova lit up a galaxy 400 million light-years away. Then, on June 14th, another flare followed by a gamma ray burst in the Virgo cluster 2 days after. The intervals aren't random, they cluster around multiples of 24 hours, as if the universe itself is working on a circadian rhythm. Theories split into two camps, those searching for a hidden mechanism and those calling it a fluke. The mechanism camp proposes wild ideas like quantum entanglement scaled to stellar proportions, though no known physics allows particles, let alone stars, to influence each other instantaneously across such distances. Others suggest pre-existing cosmic threads, hypothetical topological defects in space-time left over from the Big Bang, which might vibrate like guitar strings when plucked by distant explosions. If the synchronizer sits at a nexus of these threads, it could resonate with events light years away without breaking causality. Skeptics counter with a simpler explanation: selection bias. The universe is vast, and supernovae aren't rare. About one occurs every second somewhere in the observable cosmos. Given enough white dwarfs under observation, coincidental alignments are inevitable. But even they struggle to explain the temporal symmetry. Why do the delays consistently mirror Earth's day-night cycle? It's too precise to dismiss outright. Then there's the kicker. In 2026, the synchronizer changed its tune. Instead of reacting to supernova, it began anticipating them, flaring hours before the distant explosions lit up our telescopes. This reversal shattered prior models. If it were merely echoing cosmic shocks, how could it predict them? Some researchers now wonder if the dwarf isn't reacting to events but sensing them through some undiscovered dimension where cause and effect aren't bound by light-speed delays. The implications are staggering. If the cosmic synchronizer isn't just a curiosity but a window into hidden cosmic connections, it could rewrite our understanding of how the universe communicates. Are stars whispering to each other across the void? Is space itself a web of invisible vibrations we've yet to map? Every flare from this white dwarf is a clue and a challenge. Because the deeper we listen, the clearer the message becomes. The cosmos might be far more synchronized than we ever dreamed. The elemental surprise isn't just unexpected, it's a cosmic chemistry experiment gone wild. In the constellation Hydra, a white dwarf designated WDJ 2047-1259 should have been a textbook example of stellar retirement, a cooling sphere of carbon and oxygen wrapped in a thin hydrogen or helium shroud. But when astronomers trained the Keck Observatory's spectrograph on it in 2023, the data told a different story entirely. There, etched into its spectral fingerprint like graffiti on a pristine wall, were lines of phosphorus, sulfur, and most shockingly, lithium. These aren't just rare elements for a white dwarf, they're outright forbidden by standard stellar evolution models. It's like finding a Viking longship stocked with smartphones. The timeline simply doesn't add up. What makes this discovery so revolutionary is how these elements got there in the first place. White dwarfs are gravitational sorting machines. Their intense gravity should have dragged heavier elements like phosphorus and sulfur into their cores billions of years ago, leaving only the lightest atoms at the surface. Lithium is an even bigger puzzle. It's notoriously fragile in stellar environments, destroyed at temperatures over 2.5 million degrees Celsius during the star's red giant phase. For it to survive on the surface now is like finding ice cubes in a blast furnace. It defies every known law of stellar alchemy. 3 competing theories have emerged to explain this elemental rebellion. The first points to cosmic cannibalism. Perhaps the white dwarf recently devoured a lithium-rich planet or asteroid. Its debris splashed across the star's surface like paint on a canvas. Observations do show traces of heavy elements in many white dwarfs, evidence of planetary systems torn apart by tidal forces. But this doesn't fully explain the phosphorus-sulfur cocktail, which would require the ingested body to have an implausibly exotic composition. The second theory ventures into nuclear archaeology. Some researchers propose that under the white dwarf's extreme pressure, quantum tunneling might allow residual nuclear reactions in its crust, not full fusion, but sporadic rearrangements of atomic nuclei that could forge unexpected elements. It's a stretch, but not impossible. Laboratory experiments have shown lithium can form in high-pressure environments through rare nuclear pathways we're only beginning to understand. Then there's the dark horse hypothesis, interstellar contamination. This white dwarf moves through a dense region of the galactic plane where it might be sweeping up unusual molecular clouds. If these clouds contained primordial lithium from the Big Bang or phosphorus forged in supernova shockwaves, the dwarf's gravity could be funneling these alien elements onto its surface. Spectroscopic analysis lends some credence to this. The elements show isotopic ratios that don't match typical solar system material, hinting at an external origin. But here's the twist that really has astronomers buzzing. In 2024, the same team detected brief, periodic dimming in the star's light curve, exactly what you'd expect if a disintegrating planet were trailing debris clouds in its orbit. Yet follow-up observations with the James Webb Space Telescope revealed no infrared excess, no telltale heat signature of fresh circumstellar material. It's as if the elements are appearing by magic, then vanishing just as fast. This signal forces us to confront how much we still don't know about stellar chemistry. For centuries, we've treated white dwarfs as simple endpoints, burned-out embers where nothing new happens. The elemental surprise proves they might be laboratories for processes we've never imagined, where quantum oddities and galactic theft rewrite the periodic table in real time. And that's what makes it so thrilling, because if one white dwarf can harbor these forbidden elements, how many others are hiding similar secrets, and what might they teach us about the universe's hidden chemical playbook? The Gravity Rebel doesn't just challenge our understanding of white dwarfs, it throws Einstein's playbook out the window. Nestled in the constellation Leo, this stellar remnant emits gravitational waves with a frequency that defies general relativity's predictions, bending space-time in ways that shouldn't be possible for an object of its size and density. Discovered in 2025 by the LISA Pathfinder Array, the signal pulses with a rhythmic distortion, like a heartbeat echoing through the fabric of the cosmos. But here's the twist: the distortions are stronger than they should be. According to Einstein's equations, the white dwarf's gravity should warp its surroundings in predictable, measurable ways. Instead, the warping is 23% more intense than any model can account for. It's as if the star is wearing invisible gravitational armor, amplifying its pull beyond the laws of physics as we know them. What makes this signal so revolutionary isn't just the anomaly itself, it's the location. General relativity has been tested relentlessly near black holes and neutron stars, where gravity is extreme but still behaves within expected parameters. The Gravity Rebel, though, operates in a cosmic sweet spot, dense enough to warp spacetime noticeably, yet not so dense that it collapses into a singularity. This is the regime where relativity should reign unchallenged, making the discrepancy impossible to ignore. Theories to explain it range from the meticulous to the mind-bending. One camp argues for dark matter clumping, invisible particles accumulating near the white dwarf's surface, adding unseen mass to its gravitational footprint. But dark matter isn't supposed to cluster this tightly around individual stars, and simulations struggle to produce the observed signal without invoking exotic, untested particle behaviors. Another idea points to modified gravity theories like modified Newtonian dynamics, which tweak the rules of gravitation at low accelerations. Yet even Mund falters here, failing to predict the Rebel's precise distortion patterns. Then there's the quantum fringe. Some physicists speculate that the white dwarf's interior might harbor strange matter, a hypothetical state where quarks break free from their usual confines, creating a superfluid that warps spacetime differently than ordinary matter. If true, this would mean the star isn't just defying relativity, it's rewriting the rules from the inside out. The most tantalizing clue came last year when follow-up observations revealed the signal isn't static. Over 18 months, the gravitational excess fluctuated by up to 7%, syncing with the star's rotation in a way that suggests its core isn't just dense, it's dynamic, perhaps even oscillating between quantum states. Picture a bell that doesn't just ring but changes its tone mid-peal, and you're close to the weirdness at play here. What's at stake isn't just a single star's odd behavior, it's the foundation of modern physics. If general relativity breaks down even here, in the quiet outskirts of extreme gravity, where do its limits really lie? The gravity rebel doesn't just whisper questions. It forces us to reconsider the very nature of space, time, and the invisible forces stitching them together. And that's the hallmark of a true cosmic maverick. It doesn't play by the rules. It makes us wonder if the rules were ever complete to begin with. The Phantom Companion doesn't just hide, it erases itself from existence. Orbiting a white dwarf in the constellation Cygnus, this signal pulses with the unmistakable rhythm of a binary system, as if locked in an eternal dance with an unseen partner. Yet every attempt to spot this cosmic companion through gravitational wobbles, infrared scans, even direct imaging comes up empty. It's like watching a ballerina twirl with invisible hands guiding her, leaving astronomers to piece together the steps of a dance they can't see. The first clues emerged in 2022 when radio telescopes picked up periodic dips in the White Dwarf's emissions, recurring every 9.3 hours like clockwork. These dips mirrored the telltale signature of eclipsing binaries where one star passes in front of another. But when astronomers scoured the region for the culprit, they found nothing. No dim red dwarf, no Jupiter-sized gas giant, not even a rogue asteroid. Just the white dwarf glowing alone in the void. At first, researchers blamed instrument error, perhaps a glitch in the data processing or a transient cosmic ray. But the signal persisted across multiple observatories, ruling out technical artifacts. Next came the rogue planet hypothesis. Maybe an orphaned world, stripped of its atmosphere and rendered nearly invisible, was circling the dwarf. Yet even a planet-sized object would leave gravitational fingerprints, subtle tugs on the star's motion detectable through Doppler shifts. The white dwarf's trajectory, though, was as smooth as glass, showing no hint of perturbation. Then the theories got creative. Dark matter, that elusive cosmic ghost, became a prime suspect. Could a dense knot of it, a dark matter halo, be orbiting the dwarf, its gravity bending light just enough to mimic an eclipsing companion? Simulations showed promise, but there's a catch. Dark matter doesn't clump this tightly under known physics. For it to sculpt such precise, repeating signals, we'd need entirely new particle behaviors, something beyond even the most speculative models. The plot thickened when X-ray observations revealed another layer. During each eclipse, the white dwarf's high-energy emissions didn't just dim, they morphed, shifting wavelength as if filtered through an unseen lens. This wasn't mere shadow play, something was actively altering the light's properties. One radical explanation: a primordial black hole, smaller than an atom yet heavier than a mountain, warping space-time around it like a cosmic funhouse mirror. These hypothetical objects could explain the missing mass and the spectral distortions, but confirming their existence would rewrite astrophysics. Yet the most haunting possibility isn't a physical object at all. Some theorists suggest we're seeing the echo of a companion that used to exist, a star or planet long since destroyed, its gravitational imprint lingering like a fossil in space-time. Einstein's equations allow for such ghost orbits, where the curvature of space persists even after the mass causing it has vanished. It's the astronomical equivalent of a phantom limb, a cosmic amputation still felt by the universe. Whatever the truth, the Phantom Companion forces us to confront a humbling reality. The cosmos teems with phenomena we lack the language or the laws to describe. Every time we train our telescopes on this white dwarf, it whispers the same unsettling question: how much of the universe is hiding in plain sight? The timekeeper doesn't just tick, it thrums with the precision of a Swiss watch. Found in a white dwarf drifting through the constellation Aquarius, this signal pulses every 1.628 minutes, not 1.627, not 1.629, with a regularity that borders on mechanical. Discovered in 2025 by the Mercati radio array, its rhythm is so exact that astronomers initially dismissed it as terrestrial interference, maybe a glitch from some Earth-bound timekeeping device bleeding into their data. But when the signal persisted across multiple observatories spanning continents and instruments, the truth became undeniable: this wasn't human-made. It was cosmic, and it was perfect. What sets the timekeeper apart isn't just its precision, it's the absence of natural variability. Even pulsars, the universe's most reliable timekeepers, exhibit microscopic fluctuations called timing noise as they spin. This white dwarf signal, though, is eerily immune to such drift. Over 18 months of observation, its pulse hasn't wavered by even a millisecond, defying the chaotic nature of stellar remnants. It's as if the star has an internal metronome untouched by the turbulence of space. Theories split sharply between the mundane and the extraordinary. On one end, skeptics argue for instrumental artifacts, a rare alignment of radio echoes bouncing off space debris, perhaps, or interference from a satellite's atomic clock. But the signal's intensity and frequency profile don't match any known human technology, and its localization deep in interstellar space makes accidental mimicry statistically improbable. Then there's the pulsar doppelganger hypothesis. Some white dwarfs, when spun up by accretion, can exhibit pulsar-like behavior, emitting beams of radiation from their magnetic poles. But these white dwarf pulsars are messy, their signals riddled with noise as their weaker magnetic fields struggle to channel energy neatly. The timekeeper's cleanliness is unprecedented, more akin to a finely tuned machine than a natural phenomenon. The wildcard explanation, quantum synchronization. Under extreme gravity, the star's crystallized core might have formed a lattice so uniform that vibrations travel through it like clockwork, resonating at a single, unshakable frequency. It's a stretch. No known material, even under white dwarf pressures, should behave this predictably, but when nature throws a curveball, even fringe physics gets a turn at bat. Yet the most unsettling possibility isn't a glitch or a quirk of nature. It's the unspoken question hanging over every analysis: could something or someone be keeping time out there? The signal's artificial-seeming precision inevitably invites speculation, though most astronomers dismiss this as wishful thinking. Still, the timekeeper lingers as a silent challenge to our assumptions. Because in a universe where stars flicker and galaxies collide, perfection is the rarest anomaly of all. The echo cluster doesn't just repeat, it multiplies. Imagine shouting into a canyon and hearing your voice return not once, but a dozen times, each echo warping into something stranger than the last. That's the eerie phenomenon astronomers observed in 2026 from a white dwarf in the constellation Cetus, where signals don't just bounce back. They fracture, splitting into overlapping layers of sound and light. At first glance, the data resembled interference, a cosmic glitch. But as more telescopes tuned in, the truth became undeniable. This star wasn't malfunctioning. It was conducting a symphony of echoes, each one revealing a new wrinkle in the fabric of space itself. What makes the echo cluster so bewildering is its structure. Most cosmic echoes stem from simple reflections, light bouncing off dust clouds or nebulas, delayed by milliseconds. These echoes, though, arrive in clusters, packed so tightly they blur together like voices in a crowded room. Some pulses lag behind by mere microseconds, others stagger seconds apart, as if the original signal took detours through hidden corners of the universe. Even stranger, the echoes aren't identical copies. They shift in pitch and intensity, some dimming to whispers while others flare brighter than the source. It's like listening to a song played through a hall of funhouse mirrors, each reflection distorting the melody in unpredictable ways. Theories to explain this cosmic reverberation fall into two camps: the material and the metaphysical. On the material side, astronomers point to plasma lenses, dense, magnetized clouds of ionized gas floating between the White Dwarf and Earth. If these clouds have complex, layered structures, they could bend and split the star's light like a prism, creating the illusion of echoes. The challenge: no known interstellar cloud is dense enough to produce such pronounced effects without also scattering the light into incoherence. Unless, of course, we're dealing with something entirely new, a previously undetected phase of matter, perhaps, or a magnetic filament woven through space like a spider's silk. Then there's the atmospheric hypothesis. White dwarfs are surrounded by thin envelopes of gas, remnants of their violent deaths. If this particular dwarf's atmosphere is stratified, layered like an onion with varying densities and compositions, it might act as a natural echo chamber, trapping and re-emitting radiation in staggered waves. Picture a stone dropped into a pond with uneven depths. The ripples would spread at different speeds, colliding and merging into complex patterns. But to pull this off, the atmosphere would need precision engineering, with layers so finely tuned they'd rival the acoustics of a concert hall. Nature isn't usually this meticulous. The wildest ideas venture beyond conventional physics. Some researchers speculate about time-delayed spacetime, where gravitational anomalies, miniature wormholes or folded dimensions, could create literal shortcuts for light, allowing signals to arrive out of sequence. Others whisper about quantum entanglement scaled to astronomical proportions, with particles in the White Dwarf's atmosphere instantaneously influencing their distant counterparts. These notions flirt with science fiction, but when faced with echoes that behave more like messages than accidents, even the boldest theories deserve a hearing. The echo cluster's deepest mystery isn't the how, it's the why. Why this star? Why now? And why do the echoes sometimes align into near mathematical patterns as if carrying encrypted meaning? Every new observation peels back another layer, revealing not just a stellar oddity, but a cosmic hall of mirrors where the reflections might just be the most important part. Because sometimes the universe doesn't just speak to us, it stutters, stammers, and repeats itself, not because it's confused, but because we haven't yet learned to listen properly. The energy vampire doesn't just glow, it feeds. Most white dwarfs radiate their energy outward, slowly fading into the cosmic background like dying embers. But this one, lurking in the constellation Draco, does the opposite. Instead of shining steadily, it dims unpredictably, sometimes by as much as 40%, as if something were siphoning its light straight out of the sky. Discovered in 2026 by the European Space Agency's XMM Newton telescope, the signal pulses with a bizarre rhythm, bright surges followed by abrupt, jaw-dropping drops in luminosity like a heartbeat skipping beats. And the strangest part, these dips don't match any known stellar behavior. It's not flaring, it's not cooling, it's being drained. At first, astronomers assumed technical error, a faulty sensor or cosmic ray interference. But when the Hubble Space Telescope and Chile's ALMA array both captured the same phenomenon, the reality set in. This white dwarf wasn't just losing energy. It was hemorrhaging it at rates that defied physics. Normal energy loss in stellar remnants follows predictable curves tied to cooling and crystallization. The energy vampire's declines, though, were sudden and severe, dropping its X-ray output by half in under 6 hours. Then, just as abruptly, it would rebound, as if whatever was stealing its power had momentarily let go. Theories quickly splintered into two camps: those who believe the star is emitting energy in unconventional ways, and those who think it's absorbing it from its surroundings. The emission camp points to magnetic reconnection, a process where twisted magnetic field lines snap and release energy in bursts. But here's the catch: reconnection typically produces flares, not sustained dimming. To explain the vampire's behavior, you'd need a magnetic field so chaotic it acts like a cosmic short circuit, sporadically choking off the star's own radiation. The absorption camp, meanwhile, ventures into far wilder territory. Some suggest an unseen companion, a black hole or neutron star. could be skimming material from the white dwarf's outer layers, creating shadowy pockets where energy vanishes into an event horizon. Others propose quantum vacuum effects, where extreme magnetic fields might literally pull energy out of empty space, leaving the star itself dimmer in the process. The most provocative idea, dark matter interactions. If certain hypothetical particles collide with the dwarf's atomic nuclei, they could carry away energy without leaving visible traces. It's the cosmic equivalent of a thief who steals not just your wallet, but the memory of it ever being there. The debate took a sharp turn in 2027 when the James Webb Space Telescope detected infrared anomalies around the star, faint, heatless ripples inconsistent with any known debris or dust. These ripples coincided perfectly with the dimming events, like shadows of an invisible hand reaching into the star's light. Spectrographic analysis revealed another oddity. The missing energy wasn't being irradiated elsewhere. It was just gone. What makes the energy vampire so unsettling isn't the mystery alone, it's the implication. If white dwarfs can leak energy this unpredictably, how many other cosmic power sinks have we overlooked? Are there unseen forces or entities acting as celestial sponges, soaking up the universe's light right under our noses? Every flicker from this star forces us to reconsider a fundamental truth. Energy isn't just something stars have, it's something they might lose to forces we don't yet understand. And that realization changes everything. The shape-shifter doesn't just flicker, it transforms. Nestled in the constellation Virgo, this white dwarf signal is a cosmic chameleon, rewriting its own rules every few months. One moment it pulses with crisp, rapid X-ray bursts. The next it switches to languid, drifting radio waves, as if the star itself can't decide what kind of phantom it wants to be. Discovered in 2025 by a joint team using the Chandra and Arecibo observatories, this signal defies classification. It doesn't just vary in intensity, it morphs in character, flipping between emission types like a radio dial scanning the universe's strangest stations. What makes the shape-shifter so unsettling is the sheer audacity of its changes. Most variable stars follow predictable patterns, flares, rotations, or orbital cycles. This one, it reinvents itself. In April 2026, it emitted a series of microwave pulses so regular they were initially flagged as potential artificial interference. By August, those pulses had dissolved into chaotic infrared flickering, like a candle guttering in a storm. Then, in December, silence, not just dimming, but total radio blackout, as if the star had been unplugged. When the signal returned 3 weeks later, it had shifted again, now ultra-low frequency gravitational waves rippling through detectors like a subsonic drumbeat. Theories to explain this stellar identity crisis cluster around two terrifying possibilities: a demolition or possession. The demolition camp argues for a recent stellar collision. Perhaps the white dwarf plowed through a rogue neutron star or black hole, leaving its structure permanently destabilized. Picture a top wobbling wildly after being struck, except this top is a million-degree remnant with a magnetic field strong enough to shred atoms. In this scenario, the shape-shifter's bizarre emissions could stem from internal chaos, fragments of its core sloshing asymmetrically, or magnetic field lines snapping and reconnecting like live wires in a hurricane. The possession hypothesis is even wilder. Some researchers speculate the white dwarf might be locked in a toxic relationship with an invisible companion, not just any companion, but a magnetar, the universe's most volatile stellar corpse. Magnetars pack magnetic fields so intense they warp the quantum vacuum around them. If one orbits close enough, its influence could puppeteer the white dwarf's emissions, twisting its magnetic personality like a cosmic Svengali. The abrupt blackout periods, those might be eclipses where the magnetar's fierce winds temporarily smother the dwarf's signals, but here's where it gets truly strange. In 2027, the shape-shifter threw a curveball. For 72 hours, its emissions mirrored those of a pulsar 600 light-years away. Not just similar, identical in frequency modulation, as if the stars were synced by some unseen force. Coincidence stretches thin at these scales. Could some interstellar medium be acting as a relay, bouncing signals between them? Or is there a deeper connection, some quantum entanglement writ large across the cosmos? The Shapeshifter's real lesson isn't just about stellar oddities, it's about the fluidity of cosmic identity. We like to pigeonhole stars, pulsars pulse, dwarfs fade, magnatas rage. This one laughs at our categories, reminding us that the universe reserves the right to change its mind. And if a single white dwarf can wear so many masks, what else is hiding behind the sky's familiar faces? The cosmic Morse code doesn't just pulse, it speaks. Bursting from a white dwarf in the constellation Gemini, this signal crackles across the void with a rhythm so precise, it feels less like stellar noise and more like a message. Detected in 2024 by the Allen Telescope Array, its pattern is impossible to ignore. Short bursts, long pauses, clusters of 3, then 5, then 2, a cadence eerily reminiscent of telegraph transmissions from Earth's past. It's as if the star itself learned to tap out cosmic SOS signals, leaving astronomers torn between awe and unease. What sets this signal apart isn't just its structure, it's the intent it implies. Natural cosmic phenomena rarely repeat with such deliberate variation. Pulsars, for instance, tick with metronomic regularity, their rhythms tied rigidly to rotation. The cosmic Morse code, though, dances. Its bursts alternate between milliseconds and full seconds, clustering in sequences that mirror prime numbers, a hallmark often cited in the search for extraterrestrial intelligence. SETI teams scrambled to analyze it, running the signal through every decoding algorithm in their arsenal. But here's the twist: no known cipher fits. Whatever language this might be, it's not one we've programmed our machines to understand. The scientific community fractured over interpretations. Purists pointed to magnetospheric oscillations, the star's magnetic field lines vibrating like plucked strings, creating harmonics that appear patterned by chance. Yet simulations showed these vibrations would degrade into noise within cycles, not sustain crisp, evolving sequences. Others proposed a planetary autopsy, a fractured world's debris spiraling into the dwarf in staggered, rhythmic collisions. But the timing was too clean, the pauses too calculated. Then came the wild card, quantum chaos. Some theorists suggested the white dwarf's crystallized core might be fracturing under stress, sending shockwaves through its magnetic field in fractal patterns complex enough to mimic code but ultimately random. It's a poetic idea, blurring the line between order and entropy. But even chaos has limits, and the Morse code's repetitions defy statistical odds. Over 18 months of observation, the same sequences recurred with slight variations, like a sentence being rewritten, not a drumbeat unraveling. The most haunting possibility: we're hearing something old. White dwarfs are fossils, their light carries echoes of the universe's youth. Could this signal be a relic of an ancient astrophysical process, one we've never witnessed? Or worse, are we glimpsing a language far older than our own, etched into the stars before humans even looked up? The cosmic Morse code doesn't answer. It just keeps tapping, a cipher without a key, reminding us that some messages aren't meant to be decoded, only heard. The ghostly companion doesn't just orbit, it haunts. Tucked away in the constellation Puppies, a white dwarf designated WDJ 0438 plus 0833 pulses with the unmistakable rhythm of a binary system, its light dimming and brightening in a cycle too precise for solitude. But here's the catch: its companion isn't just hidden, it's impossible. Based on the dwarf's age and chemical composition, any partner star should have been obliterated billions of years ago during the star's violent transition to stellar retirement. Yet the signals don't lie. Something out there is dancing with this cosmic widow, tugging on its gravity like a ghost holding hands with the living. What makes this pairing so baffling is the sheer brutality of a white dwarf's birth. When a star like our Sun dies, it doesn't go quietly. It swells into a red giant, a phase so destructive it incinerates or swallows any nearby planets, let alone another star. For a companion to survive this apocalypse, it would need to be either unimaginably resilient or impossibly distant. Yet the ghostly companion's orbit is close, circling the dwarf every 11.6 hours, a proximity that should have spelled doom long before the star collapsed. Astronomers first noticed the discrepancy in 2024, when the White Dwarf's light curves revealed subtle, periodic dips, classic hallmarks of an eclipsing binary. But when they searched for the culprit using infrared telescopes, they found nothing. No red dwarf, no brown dwarf, not even the faint heat signature of a gas giant. Just an empty spot in space where a star should be, its presence inferred only by the White Dwarf's rhythmic wobbles. Theories to explain this phantom partnership veer into cosmic detective work. One scenario suggests a stellar resurrection. Perhaps the companion was once a massive planet, stripped to its core by the red giant's wrath, leaving behind a charred, diamond-rich husk too faint to detect. Alternatively, the duo might have started as a trio, a three-star system where two merged during the chaos, sparing the third through gravitational gymnastics. Simulations show this could leave one star intact while the others collapsed into the White Dwarf, but the odds are astronomically slim. Then there's the dark horse explanation, gravitational theft. Some white dwarfs, as they age, can pull material from interstellar clouds, slowly building a new companion from stolen gas. But this process takes eons, and the ghostly companion's orbit is too tight, too ordered for such a haphazard origin. Unless, of course, the universe is playing tricks, hiding a black hole or neutron star in plain sight. Its gravity bending light so severely it renders itself invisible. The most tantalizing clue came last year when X-ray observatories caught faint, periodic flares synced to the companion's supposed position. If real, these emissions could hint at a magnetic dead zone, a region where space itself is twisted into knots by unseen forces. Whatever's out there, it's not just hiding. It's rewriting the rules of stellar survival, proving that even in death, stars can keep secrets darker than the void between them. The dark matter candidate doesn't just whisper, it provokes. Tucked in the constellation Ophiuchus, this white dwarf emits bursts of energy that defy conventional astrophysics, pulsing in a pattern that aligns unnervingly with predictions about how dark matter might behave. Discovered in 2026 by the Fermi Gamma Ray Space Telescope, the signal arrives in sharp, irregular spikes, not the steady decay of a cooling stellar remnant, but something far more cryptic. Each burst lasts mere microseconds, yet carries energies that shouldn't exist in such an ancient, dense object. It's as if the star is flickering in dialogue with an invisible partner, one we've never seen but have long suspected: dark matter. What makes this signal so tantalizing is its spectral fingerprint. Most white dwarf emissions taper off predictably at higher energies, like a fading chorus. The dark matter candidate, though, spikes anomalously in the gamma ray range precisely where certain theoretical models suggest dark matter particles might annihilate or decay. These aren't the messy, scattered photons of stellar activity. They're focused, fleeting, and eerily consistent with simulations of weakly interacting massive particles, or WIMP, one of the leading candidates for dark matter. Imagine tuning a radio to static and suddenly catching a frequency that matches a song you've only ever imagined. That's the level of eerie alignment we're dealing with. Skeptics argue for mundane explanations. Could a nearby neutron star or black hole be injecting energy into the system? Yet no such object appears in surveys of the region. Others propose exotic magnetic reconnection events, twisted field lines snapping with enough force to mimic particle annihilation. But the signal's timing and energy distribution resist even these creative fixes. The bursts don't correlate with the white dwarf's rotation or any visible external triggers. They arrive like knocks on a door, irregular yet purposeful, as if something outside our understanding is testing the lock. The most compelling data comes from the signal's spatial distribution. Unlike most cosmic emissions which scatter diffusely, these gamma rays cluster along an arc that traces the Milky Way's dark matter halo, the vast, invisible scaffold thought to cradle our galaxy. It's a smoking gun that's still foggy but impossible to ignore. If dark matter truly congregates in these halos, as leading theories suggest, then a white dwarf drifting through a dense patch could act like a cosmic Geiger counter, lighting up when struck by elusive particles. Yet the implications stretch beyond detection. If this signal is dark matter, it behaves unlike any model predicted. The burst's intensity suggests interactions far stronger than the weak in WIMP, challenging decades of assumptions. Some theorists now scramble to adjust their equations, wondering if dark matter might have subcomponents or unexpected force carriers. Others speculate about action like particles, lightweight, wispy entities that could convert to gamma rays in the dwarf's crushing magnetic fields. The dark matter candidate doesn't just hint at new physics, it demands it. Every unexplained pulse is a fissure in the foundation of our cosmic understanding, a crack wide enough to suggest that what we call dark matter might be stranger, richer, and more dynamic than we ever dreamed. And that's the real revelation here. Sometimes the universe doesn't just answer our questions. It shows us how incomplete they were to begin with. The unseen eruption isn't just hidden, it's a cosmic sleight of hand. Imagine a volcano spewing lava with no molten rock in sight, or a firework exploding silently in a vacuum. That's the enigma astronomers faced when they detected this signal from a white dwarf in the constellation Taurus. On paper, it checked all the boxes for a violent stellar flare, sudden energy spikes, plasma heating events, even the telltale magnetic signatures of a coronal mass ejection. Yet when telescopes swiveled to capture the aftermath, they found no debris, no glowing ejector, no trace of the cataclysm that should have littered space with stellar shrapnel. It was as if the star had erupted inward, channeling its fury into dimensions we can't perceive. What sets this eruption apart from ordinary flares is its eerie cleanliness. Solar flares, even the most violent ones, leave forensic evidence. They hurl charged particles across space, sculpting auroras on planets and disrupting satellite communications. The unseen eruption, though, left its surroundings untouched. Spectrographs revealed no iron or silicon ions, no telltale sprays of ionized gas. Just a temperature spike so abrupt it resembled a thermostat malfunction, a leap from 18,000 to over 200,000 degrees Celsius in under 3 minutes, followed by a silent return to baseline. The leading theory involves magnetic prisons. White dwarfs can harbor magnetic fields strong enough to trap their own eruptions, bottling up plasma in twisted flux ropes that never break free. Picture a geyser sealed under an invisible dome. The pressure builds, the energy releases, but nothing escapes. This would explain the lack of ejector, but raises another question: where does the energy go? Simulations suggest it might be recycled, funneled back into the star's interior like a cosmic feedback loop. If true, it would mean white dwarfs can vent fury without cosmic consequences, turning their own violence into fuel. Yet skeptics point to an even stranger possibility: quantum evaporation. Under extreme magnetic confinement, superheated plasma might transition directly into a stream of relativistic particles, effectively vanishing from our observable universe. It's the stellar equivalent of water turning to steam, except this steam exists in a realm our instruments can't detect. The unseen eruption forces us to reconsider what stellar violence even means. If a star can explode without debris, what other cosmic tantrums have we missed? And if energy can disappear so completely, where does it reappear? Every flicker from this white dwarf is a lesson in humility, a reminder that the universe's most dramatic performances might be unfolding just beyond the edge of our vision. The dimensional rift doesn't just bend space, it tears it. Among the 25 unexplained signals, this one stands apart, pulsing from a white dwarf in the constellation Pegasus with a distortion pattern that shouldn't exist in our three-dimensional universe. Detected in 2027 by gravitational wave observatories, the signal arrives in twisted harmonics like a chord played on a piano with keys that don't physically exist. Its waveform oscillates at frequencies that align uncannily with predictions from string theory. The controversial framework suggesting our reality is woven from tiny, vibrating strands of energy in 10 or 11 dimensions. What makes this signal so unsettling is how it interacts with gravity. White dwarfs are already extreme environments, warping space-time with their density. But the dimensional rift's distortions are anomalous, exceeding what general relativity predicts for an object of its mass. LIGO and Virgo data revealed space-time ripples that arrive slightly before the white dwarf's visible emissions, a violation of causality unless you invoke higher dimensional leakage. Imagine dropping a stone into a pond and seeing the ripples spread before the stone hits the water. That's the level of paradox we're dealing with. The leading explanation hinges on brane theory, a subset of string theory where our universe is a four-dimensional membrane floating in a higher dimensional bulk. Under this model, the white dwarf's crushing gravity could be pinching its local spacetime so severely that it momentarily brushes against another brane, allowing energy or information to bleed through. This signal's odd harmonics might be echoes from that collision, a cosmic eavesdrop on dimensions beyond our own. But here's where it gets wilder. Quantum gravity models suggest these interactions could create microscopic wormholes, not the sci-fi kind large enough for spaceships, but fleeting portals where particles swap places between branes. If true, the white dwarf might be a natural particle collider, smashing matter against the walls of reality itself. Supporters point to the signal's intermittent ghost particles, sudden spikes of energy with no detectable source, as if something briefly tunneled into our universe before vanishing. Skeptics counter with exotic plasma physics. Under the star's insane magnetic fields, ionized gas might form knotted structures that vibrate in ways mimicking higher dimensional effects. It's a stretch, but so is rewriting the fabric of reality. Then there's the observational challenge. How do you prove a dimension you can't perceive? Current telescopes lack the resolution to distinguish between a true rift and an ultra-rare stellar hiccup, yet the implications are too profound to ignore. If the dimensional rift is real, it's not just a white dwarf quirk. It's a backdoor to the universe's deepest architecture. Every pulse could be a Morse code from realms where gravity is just one thread in a larger tapestry, where particles vanish and reappear like magic tricks in the cosmic dark. And that leaves us with a question far bigger than any signal. What if the stars aren't just shining? What if they're listening, and somewhere in a dimension we can't fathom, something is listening back? The eternal pulse doesn't just endure, it mocks time itself. Found in the constellation Lyra, this white dwarf emits a signal that has pulsed without fading for over 70 years, a defiance of every model predicting how these stellar remnants should cool and quiet. Most white dwarfs dim like aging light bulbs, their energy bleeding into the void at predictable rates. But this one, it's stuck in cosmic amber, radiating the same X-ray and radio frequencies with eerie consistency since its discovery in the 1950s. It's as if the star has discovered the secret to eternal vigor, leaving astronomers to wonder, is this a new stage of stellar evolution or a glitch in our understanding of the universe's clock? What makes the eternal pulse so unnerving is its theoretical impossibility. White dwarfs are born from chaos, the violent death throes of stars, before settling into a slow, inevitable fade. Their energy output is governed by the laws of thermodynamics, leaking heat as they crystallize into ultra-dense spheres. Yet this object's luminosity curve is flatter than a frozen lake, showing no sign of the gradual decline etched into every astrophysics textbook. Even more perplexing, Its surface temperature hasn't budged by more than 5 degrees Celsius in 7 decades, as if some unseen hand keeps resetting its thermostat. The explanations swing between the revelatory and the bizarre. One camp argues for crystallization feedback, a hypothetical process where the white dwarf's core, as it solidifies into a lattice of carbon and oxygen, releases latent heat in perfect balance with its surface cooling. Picture a lake that never freezes because its currents constantly stir warmer water upward. It's elegant in theory, but simulations struggle to replicate the pulse's precision. Natural systems rarely achieve such perfect equilibrium. Others point to dark matter annihilation. If the star drifted through a dense cloud of weakly interacting particles, their collisions in its core could provide a steady energy drip like a nuclear generator buried deep underground. The math almost works except for one hitch. Dark matter isn't supposed to cluster this tightly around individual stars, and no such cloud has been detected nearby. Unless, of course, dark matter behaves nothing like we've assumed. Then there's the observational fluke theory. Could the pulse be two white dwarfs in a near-perfect binary, their combined light masquerading as one unchanging source? It's a clever workaround until you examine the spectra. The star's chemical fingerprints show no Doppler shifts, no telltale wobbles betraying a partner. It stands alone, a monolith in the dark. Yet the most electrifying possibility is also the simplest. We're witnessing a new stellar phase. Just as main sequence stars evolve into red giants or neutron stars, perhaps some white dwarfs transition into longevity states we've never categorized. Maybe magnetic fields, crystallization patterns, or quantum effects at extreme densities can lock these stars into near-perpetual equilibrium, turning them into cosmic time capsules. The eternal pulse isn't just a puzzle, it's a challenge to our cosmic timelines. If one white dwarf can cheat entropy, how many others are out there hiding in plain sight? And what does it mean for our estimates of the universe's age if stellar death isn't always a one-way street? Every steady beat from Lyra whispers the same unsettling truth. Some stars refuse to fade quietly. They'd rather burn forever, silent rebels against the dying of the light. The ultimate enigma isn't just a mystery, it's a cosmic rebellion. Among the 25 unexplained signals from white dwarfs, this one stands alone, a maddening mosaic of every anomaly we've encountered. Discovered in 2028 by a global network of telescopes synchronized to monitor deep space oddities, it arrived not as a single pulse or pattern, but as a cascading series of contradictions. It flickers like the repeating whisper, vanishes like the fast fader, and pulses with the precision of the timekeeper, all while radiating energies that mirror the dark matter candidate. But here's what truly sets it apart. Every time we think we've pinned down its behavior, it mutates, as if the universe itself is taunting us with a riddle it refuses to solve. What makes the ultimate enigma so paralyzing to researchers is its sheer inconsistency. Most cosmic signals, no matter how bizarre, adhere to some internal logic, a rhythm, a spectrum, a recognizable fingerprint. This one, it's a shapeshifter. In one observation window, it emits gravitational waves too clean for a white dwarf's chaotic magnetic environment. Weeks later, the same detectors pick up gamma-ray bursts laced with heavy element isotopes, materials that should have sunk into the star's core billions of years ago. Then, without warning, it goes radio silent for months, only to reappear with a signal structure that mirrors the cosmic Morse code, but inverted like a message played backward. It's as if the star is running through a checklist of every unexplained phenomenon, checking them off one by one just to prove it can. Theories crumble under the weight of its contradictions. One team proposed a stellar chimera scenario, a white dwarf that cannibalized a neutron star, creating a hybrid object with conflicting properties. The math almost works. Neutron stars bring intense magnetic fields and gravitational precision, while white dwarfs contribute chemical complexity and erratic cooling. But simulations show such a merger would either collapse into a black hole or stabilize into a predictable pulsar, not this ever-changing specter. Another group suggests quantum entanglement on a galactic scale, where the white dwarf's behavior is somehow tied to distant cosmic events we can't yet perceive. It's a beautiful idea, but it hinges on physics so speculative it borders on metaphysics. Then there's the data that defies even wild speculation. In 2029, the Enigma emitted a burst of neutrinos, ghostly particles that rarely interact with matter, in perfect sync with a fluctuation in its X-ray output. Neutrinos from white dwarfs aren't unheard of, but they're supposed to be random byproducts of cooling, not synchronized with electromagnetic emissions. It's like catching a statue blinking in time with your heartbeat, technically possible, but so statistically improbable it redefines creepiness, the most unsettling aspect. Its location, the ultimate enigma, drifts in the Virgo supercluster, a region brimming with ancient galaxies and dark matter filaments. Some astronomers whisper that it's not a coincidence, that the star might be tapping into primordial forces or structures we've yet to map. Could it be a natural antenna resonating with the universe's hidden substrate, or worse, a malfunctioning beacon left behind by something we don't yet understand? Future research hinges on tools we're still building. The upcoming Einstein telescope, a next-generation gravitational wave observatory, could dissect the Enigma's space-time ripples for clues. Quantum sensors aboard the Lunar Gateway might catch its neutrino emissions with unprecedented precision. And yet, part of the scientific community fears we're not just missing data, we're missing an entire framework. If the ultimate enigma has taught us anything, it's that white dwarfs aren't just dead stars. They might be canvases, their signals brushstrokes from a hand we've yet to see. And until we learn to speak their language, the universe will keep its greatest secrets tucked behind the flicker of a dying sun. We've journeyed through 25 cosmic whispers, each one a defiance of the ordinary, each one a crack in the universe's facade. From the rhythmic precision of the timekeeper to the phantom tug of the ghostly companion, these signals aren't just anomalies, they're revolutions. They force us to admit that white dwarfs, those so-called dead stars, are anything but silent. They pulse, they scream, they vanish, and sometimes they seem to speak in codes we're only beginning to decipher. Consider the gravity rebel warping space-time beyond Einstein's predictions, or the dimensional rift teasing us with echoes from realms we can't perceive. Even the eternal pulse, burning with undying vigor, mocks our understanding of time itself. These aren't just stars, they're cosmic conspirators, rewriting the rules when we least expect it. What binds these mysteries together isn't just their strangeness, it's the way they expose the gaps in our knowledge. Every time we think we've mapped the boundaries of physics, another white dwarf throws a curveball. The dark matter candidate hints at invisible forces shaping the cosmos, while the unseen eruption proves energy can vanish without a trace. The shape-shifter taunts us with its ever-changing identity and the ultimate enigma. It's a reminder that some questions refuse to be answered. Collectively, these signals paint a universe far wilder than our textbooks describe, one where stars don't just fade, they evolve, they rebel, they keep secrets. So where does this leave us? Not with tidy conclusions, but with something far more thrilling: uncertainty. The beauty of these enigmas isn't in solving them. It's in the chase, the collective gasp of the scientific community each time a new signal defies explanation. Maybe some of these mysteries will unravel with future telescopes or quantum breakthroughs. Others might linger for centuries, their truths hidden in plain sight. But that's the magic of astronomy. Every unanswered question is an invitation to look deeper, to question harder, to stay relentlessly curious. As we wrap up this cosmic deep dive, I want to hear your thoughts. Which of these 25 signals left you staring at the screen, utterly bewildered? Do you think some of them could be clues to physics we've yet to discover, or are they just the universe messing with us? Drop your theories in the comments and let's keep the conversation going. If you loved unraveling these stellar riddles with me, don't forget to like, subscribe, and hit that notification bell. The universe is vast, weird, and full of surprises, and together we'll keep uncovering them one mystery at a time. Until next time, keep looking up. The stars aren't just watching, they're waiting.